Alright, so another strategy of keeping the tree balanced is to implement what we call the red-black tree. And that's a binary search tree that has some additional rules on it. Now, every node in that type of tree is assigned a color. Colors either red or black. And the rules involve state that no red node can have a red child. The root has to be always black. The external nodes, which are the empty left and right subtrees, those are always black. And the height of the tree, from the black height of the tree from the root to the external nodes, must be the same throughout the tree. So once those rules are intact, then we have a good red-black tree. Otherwise, we need some fixing to get the RB tree back up. Now, the process of inserting into a RB tree. We're going to be doing the second group of tutorial questions. We won't be looking at the first group that looks at proving the properties. So go to the beginning of page 3. So we first ask what the time complexity of recalling a 4-node critical cluster is. Let me refresh your memory what a critical cluster is. When you're inserting into the RB tree, you're going to put the new node in as a red node. Now, if the new node ends up tagged onto a red child, then remember that, let's say this is somewhere in the middle of the tree, that has a root somewhere. I'll give it a value, say 10 for argument's sake. This is 12 for argument's sake. And this may be 14 for argument's sake. Because the insertion rules for binary search trees are pretty much the same, but they are passed on to red-black trees. It's just that red-black trees have some additional rules on them. So this is an RB tree and you've put in the new node here. Remember that there is the constraint that no red node can have a red child. Now, a cluster can be thought of a black node with all the red nodes attached to it. Alright? If the cluster has a height of 1, then everything is good. If the cluster has a height of greater than 1, the cluster becomes critical and needs to be fixed. So in this case, we have a 3-node critical cluster. And how do we do that? How do we fix that? We rotate to fix a 3-node critical cluster. Now if we have a 4-node critical cluster, we need to recolor. So this is fixed by rotating something like that. 12 in. Remember that this will now be small, medium, large. So medium would be 12, so 12 would end up in the root of the cluster, 10 a bit to the right, 14 to the left. If you had a 4-node critical cluster, use the same values. And you had 8 here. Then you recolor that. So you end up with 10 at the root of the cluster. The root of the cluster becomes becomes red from black, and the 2 children of the root become black. So that would be the new organization of the cluster. If this is the critical cluster with 4 nodes, recolor that. Where is missing?
No. I tried to remember that. Because I know the circles are the red.
Circles are
So
red, squares
children,
are black.
Black children and then.
Right. Alright, so the question we need to answer is what's the time complexity of recalling a 4-node critical cluster? Theta n, theta log n. You said 4? You mean 4 steps?
You take, well, you take about 4. Theta.
It would take a certain number of steps, yes. But the important thing to understand is that it takes the same number of steps all the while to recolor. Agreed? Which makes it a constant time process. So it can be described as a theta 1 process. So
it doesn't matter how many steps you're doing, but because it's constant, it's a theta 1.
Constants fall out when we look at the asymptotic, those asymptotic functions.
Okay.
So theta 5 is theta 1, right? So the answer to question 1 is that it's a theta 1 process. Now, if n is the number of nodes in the RB tree, how many levels up may the fixing of a 4-node critical cluster eventually propagate? If you look here, when we did this recoloring fix, the root node became red. Could that have other implications?
Well, it did because
suppose the parent of this was red.
right.
Then you have to change.
Then we'd have to do another fix. So in the worst case, we could actually have the critical cluster propagating up to the root of the tree. And it could propagate up log n steps. So we can actually propagate up log n levels, which makes that the worst case time complexity of insertion into the tree.
Stick up in.
Mm-hmm.